Have you ever wondered how digital signal processing is implemented on FPGA and SoC? How can we efficiently filter signals, generate waveforms, or perform fast Fourier transform in real time? If you're an engineer working on FPGA-based DSP or just starting with Xilinx tools, you are in the right place. DSP is everywhere: communications, radar, audio processing, and more. And implemented on hardware can be quite challenging. Luckily, FPGA vendors like Xilinx provides quite powerful solutions. The DSP IP cores like FIR and CIC Compiler, DDS Compiler, Fast Fourier Transform. But understanding how to configure it and use it properly, it's a key to unlocking their full potential. This course gives you hands-on practical approach to master Xilinx DSP IP cores. Here you will learn how to simulate DSP IP cores with Vivado testbenches and analysis in Python, how to integrate DSP IP cores into FPGA design and run it on development board, how to develop standalone embedded C application to interface with DSP IP cores, and finally, how to automate Vivado and Vitis workflow with STL and Python scripts. I've worked extensively on FPGA-based DSP and I know the challenges. That's why I designed this course to be as practical and beginner-friendly as possible, avoiding unnecessary complexity and focusing on what really matters. If you are ready to master Xilinx DSP IP cores and bring your FPGA experience to the next level, join me in this course and let's get started. I am using the following setup in order to run all projects from the workshop. This is a PowerShell, updated version of PowerShell that I am running on Windows terminal. In PowerShell, I have a default version of Python. In my case, it's a 3.9.13 version with two external packages. NumPy package in order to read binary files and operate with NumPy arrays, and matplotlib package in order to plot testbench simulation results. Besides that, I have installed here Vitis and Vivado. Let's take where is my path? Vivado. Yeah, so here is my path to Vivado installation folder, to Vitis high-level synthesis by default, and to Vitis. So basically that's all we need in order to start with the workshop. Let's take a look on the folders that I'm using in this workshop, folders and sources. So before I will start with explanation, I would like to mention that this workshop can be split into three main workflows: simulation with Vivado, designing with Vivado, and embedded C application creation with Vitis. So therefore, all sources and folders here are designed in order to run and automate all these three workflows. All the three workflows for 4 DSP Xilinx IP cores. It's CIC, DDS and FIR compilers, and Fast Fourier Transform. Let's take a look on folders and files that I'm using within workshop. So first, it's an auto folder. In auto folder here I have several Python scripts. It's a Python script for every workflow, namely simulation, for example, Vivado and Vitis. Besides that, here I have clean script in order to clean certain build generated folder or all folders, and simple GUI if you prefer to work with graphic user interface instead of command line tool. So the next folder here, it's a common folder. In common folder I have Verilog file. This is the wrapper that is used during simulation and Vivado design. This file is used in order to interface some of these IP cores with AXI-DMA. Besides that, here I'm using Verilog header, where I have a task, and task it's a test cases for test bench for all 4 IP cores. So therefore, with this file, I can generate different kind of signals. It's a sinus, cosinus, for example, chirp signal, noise, or delta function. So any signal in order to exploit any of these IP cores. The next folder here, it's folder IP underscore and then IP core. So this is a folders that subfolder that is designed to work with certain DSP, Xilinx DSP IP core. Let's consider as example IP underscore kick folder. So this folder consists of 2 subfolders. It's a TB and TCL folder. In TB subfolder can be found Verilog test bench for kick compiler and waveform for Vivado simulation. In TCL file can be found 2 files. It's a 2 TCL files in order to create Vivado design with integrated System ILA, and in order to export XA file for Vitis embedded platform component and embedded application. The last but not least, it's a C source. So every folder consists of C sources. This C file is used in order to create embedded application to interface with DSP IP cores instead without operation system. So this is a standalone, so-called standalone mode. So basically, that's also every of this IP core consists of the subfolders and C applications. So next folder, it's a Py folder here. So in Py folder, several Python scripts in place. So this script is using in order to read binary file produced during test bench during Vivado simulation. So this script is using for every IP core. There is a corresponding Python script in order to read the binary file and to plot results for further analysis. Besides that, here I have DSP underscore sim TCL file. So this common file is used by Vivado to create a Vivado simulation project for one of the desirable IP core here. And the last file, it's a create Vitis Py script. This script is used by Vitis in order to create platform component for standalone application and embedded standalone application based on C sources that is placed in every of this IP underscore folder. So also here I have a README file with short instruction how to work with all these files, and also before you will start, you also will need to let me open this README file. Before you will start, you also will need to clone Digilent Vivado board files. Since my development board it's Arty Z7-20, and therefore in order to create Vivado project, these board files are required. So here is a short instruction how in 3 steps you can clone the repository, go to this folder and copy all board files into your Vivado installation folder. That's all. Quite simple setup, very easy to work. Let me demonstrate how to work, for example, with GUI interface. In order to work with GUI interface, I will need to run GUI launcher.py, and therefore a small window appears here. So, and where you can choose first a target. It's one of this IP core, and then you can run Vivado or simulation, Vitis, or clean, for example. And for clean also there are several targets. All you can clean all create folders, or you can temporary folders, or you can create, or you can clean certain workflow, for example, simulation, Vivado, or Vitis. Also, I would like to mention that it's impossible to run Vitis until Vivado project will be created. So why so? Because during Vivado designing, XA file will be exported, and this XA file is used by Vitis in order to create platform component and embedded application afterwards. In order to simulate FIR Compiler, Python script, it's a run _simpy file with FIR target should be run. So what this script does? So this script opens Vivado ADI with integrated FIR compiler, where I have 4 instances of FIR compiler. I will explain later why do I need 4 instances. And with Verilog test bench, Verilog header that I mentioned during requirements and setup explanation, and with a waveform viewer where I already have preserved settings to analyze input and output of all FIR compiler instances. Let's take a look on our folders. We need to open one more folder here. Let me open another window. After I run sim file, so build folder will be created. After I run simulation workflow, this build folder will be created. If we take a look on this build folder, there is a sim subfolder with project FIR compiler. This is a FIR, since a FIR target was specified. Besides that, here will be created several logs files. So for example, for test bench simulation.log file will be created that can be read in case of any error. And in this log file, this error will be written in case, for example, if your Vivado is failed. Okay, so simulation starts. As I mentioned, I have integrated here a where viewer. In this wave viewer, you can see input file and several outputs. So this is the output from all 4 instances. Let's take a look on sources that I am using during simulation and how I'm doing this simulation. So, as I mentioned already, I am using here 4 FIR compiler instances, and every instance here consists of certain filter type. For example, here I have like normal or regular FIR filter, namely bandpass filter. So this is a filter that I have with predefined COE file. COE it's coefficients, so it means that coefficients here is hard coded, and frequency response can be seen here. So by specifying this COE file, you can define your own frequency response. In my case, it's a band pass filter, so it means that this filter will pass certain frequency harmonics and certain harmonics will be suppressed. So, also from settings here, I would like to pay attention on data path options. So where I have single signet input and therefore signet output, and I'm using here full precision, so namely 32 bits. And another quite important stuff here that I'm here have a data channel options. It's a packet framing with enabled output terarium. So I am doing this in order to interface the IP core with, for example, AXI DMA. So this is a full AXI stream interface with data and with master and with slave AXI stream slave interface. So this can be seen from simulation results. This is the input file. Input as an input signal. As input signal, chirp signal here is used. Chirp signal with frequency started from 0 MHz up to 20 MHz. So therefore, bandpass filter will pass only frequencies within its frequency response, and it can be seen in time domain here. Another FIR compiler instance, it's a filter with filter type Gilbert. So this this instance will perform Gilbert transform and create from real part of the signal two parts, real and imaginary part. So therefore, for example, real part here is a 16 bits, and then outputs it's a 32 bits, 16 bits per part. So real and 30 bits per imaginary part. Filter also required frequency response that coefficient, that can be found in Gilbert COE file and can be seen here. So basically, this is a rectangular frequency response with some distortion, so in zero frequency harmonics. About implementation, it's completely the same as for bandpass filter, just with excluding this outputs. So because output I using here a truncate significant bin, so therefore my output width per real or per imaginary part is a 16 bit. That's why I have here 32 bit width of this bus. Besides that, here also I'm using packet framing in order to interface the IP core with XDMA for efficient data transfer. So, and two more options here, it's a decimator and interpolator. So both decimator and interpolator are using rate equal to 4. So it's a decimation factor or decimation rate value 4 and interpolation rate value 4. Both filters also require its own coefficients. So frequency response can be seen here. So for both filters, I created also a packet framing in order to interface with XDMA. And in simulation, let me open interpolator. And for simulation here, for simulation, so how I'm working with this simulation. So as input, so this input signal goes to decimator. After decimator output goes to interpolator input, and therefore output of the interpolator, it's interpolated output of decimation of decimator, or decimation filter. Let's take a look on timing diagram here, and afterwards I will explain other sources that I'm using during my test bench. So here I have input signal, it's a chirp signal, a bandpass that I already mentioned, then a Gilbert transform. Here I would like to pay attention on amplitude, that amplitude of input signal and amplitude of output signals from Gilbert transform is the same, so there is no amplitude distortion. This is a decimator. So since decimator with factor 4, it means that if you have sample frequency equal to 100 megahertz with decimation factor equal to 4, it will be reduced into 25, and therefore half of 25, it's 12.5 megahertz. It's like frequency response will be used. In this case, all harmonics behind, so all harmonics that exceed 12.5 will be filtered out. And here can be seen also interpolator output. So for interpolator, I'm using decimated signal, and it can be seen that interpolated signal has more smooth compared to decimated signal. So what kind of files I'm using for FIR compiler simulation? First of all, this is a test bench. So test bench file was included 4 instances of all 4 instances for FIR compiler. I was very frequently asked, for example, why I'm not using block design here. So yes, I am not using here a block design. I integrate IP core directly into my test bench. So I am doing this because it's quite simple, because all IP cores here, all instances operates with AXI stream interface, and AXI stream interface is quite simple compared to AXI interface That's why I prefer to use here directly just test bench Verilog simulation, but not, for example, block design. So besides that, here I have coefficient files for all 4 instances. I have here a Verilog header. In Verilog header, I have specified not only timings, but also different test cases. So these test cases, as I mentioned, it's a common file for all test benches, so it can be, so this test cases, it's a signal for FFT transform, for fast Fourier transform. It's signal like a sinus signal, like a chirp signal, like a noise signal, like delta signal also, and delta function signal, or for example, it's a phase signal for DDS compiler. In test bench, I can specify, I can call any of these tasks in order to generate certain signals. So after the simulation completed, several output binary files will be created. Let's take a look on this binary files. So they are placed into build folder. So here can be seen four binary files. Sorry, one is an input file, and 4 files. So corresponding for it's a bandpass output. It's interpolator, decimator, and Gilbert output. In order to read and plot this file, so only one script, Python from Py folder should be called. So this it's Py and FIR Compiler, since we are working with FIR Compiler. Basically, the script will reproduce the same result and will show the same result as simulation. So let's take a look. Let's start with input signal. So this is the input signal in time and frequency domain. As I mentioned already, it's a chirp signal starting with 0 MHz and up to 20 MHz. This is the only real part of the signal. Okay, let's take a look on the bandpass filter. So bandpass output can be seen on this plot. So it's like like it was seen during simulation in waveform viewer. Here we have in time domain we have signal with suppressed harmonics out of frequency response, and here can be seen this frequency basically response as well. Let's take a look on the Hilbert. Here can be seen output of Gilbert transform. So real and imaginary part of input signal. I would like to pay attention one more time that there is no amplitude distortion. So input amplitude was a little bit exceed 15,000. So, and here is the same. In the beginning, there is a little bit, so because filter has a frequency response with some distortion in area of frequency, zero frequency harmonics. So, and here is the spectrum of the signal. And two last plots, it's a decimator and interpolator. I would like to mention that factor or rate for both, for either simulation or for decimation or interpolation, it's a 4. So therefore our sample frequency is 100 megahertz, and for decimation this frequency will be downsampled to 25 megahertz. And besides that, FIR decimator has its own pulse characteristic, its own coefficients that will restrict in signal with 10 megahertz. It's like low pass filter, and therefore always within this 10 megahertz will be passed decimator output. So this output will be is received as input in interpolator, and this is can be seen the outcome here. The signal is more smooth, and yeah, and by the way, interpolator also has low pass filter implemented. So with this coefficients, with a little bit more, I guess maybe like 10 megahertz, maybe 12.5 megahertz. So basically, these coefficients can be changed by editing these COE files for every FIR compiler instances. Also, sorry, I forgot to mention about, let's compare, by the way, also another very important thing that I failed to mention here. It's an amplitude, as I mentioned. So this is amplitude. So this is a frequency, this is a in frequency domain representation of input signal. And it can be seen that after Hilbert transform, we have increased here magnitude in the frequency domain. So why basically so? So since for FFT transform only real part used for input signal, but for output signal, both parts, real and imaginary, were used. So therefore, amplitude of the output signal frequency domain will rise in 2 times. So 2 times, if yeah, we can calculate here. So 2 times it means around 6 dB. Look, and then should be multiplied by 20, about 6 dB. So, and as can be seen, for example, here from plots, it's around 55 dB, and here we have 61 dB. So that corresponds basically a theory. Let me demonstrate how test case can be changed. I will close all these plots. Let's go to Verilog test bench, so where test signal was defined. So, for example, instead of chirp signal, another signal, this is a, like, let's consider a noise. Here I have, for example, I have here a noise, simple noise can be used here. So to do this, all we need is just to modify this. So, and also I failed to mention about one also very important thing here. This is how I define these test cases. As argument here, using number of samples, it's the length of my input signal, and besides that, here I have a flag that can be either 1 or 0. So what does it mean for this flag? This flag allows to, if it's a 0, it means that valid signal, the valid signal for access stream, like it's here, for example, can be seen, has it's a constant, so without any interrupts. But in embedded systems, it's very often, for example, master can be busy, and therefore it will drive ready signal, but valid will be the same. So, and therefore, in order to verify access stream interface, here I have also implemented this feature. If I specify, for example, 1 here, this valid signal will have random pauses when it goes into low level. Let's take a look how it looks like. So I did modification of FIR Compiler test bench Verilog file, and afterwards I just relaunch full simulation. It takes time to launch all steps. This feature is quite, this option is quite useful if you would like to do not only signal analysis for your embedded system, but if you would like to also do analysis for your access stream interface. Okay, let's start and let's take a look how it looks like. So as you can see here, though, the valid signal becomes so not only, it becomes more with pauses, with low level, with random values, so in low level. But of course, it also for Master interface, also valid signal in master interface also will have the same behavior as input signal. Let's take a look. So since we still have our simulation. Okay, so it's done. If it's done, we can run Python script in order to do analysis one more time. So this can be seen here. So let's start with input signal. Where is this? Okay, so here input signal, it's a noise. It's a noise, and this is a spectrum of noise. We can take a look also on bandpass filter. Yeah, so bandpass filter, we can see how some harmonics were suppressed, how noise was suppressed out of frequency response here. So we can also take a look on Gilbert transform, on interpolator, on decimator, sorry, it's decimator and interpolator. Here also can be seen, and Gilbert transform. Yeah, so Gilbert transform is here. So whereas all harmonics is shifted by 90° in angle, I guess maybe in phase, 90° in phase. Okay. So therefore, any test case can be basically set by using this Verilog header. Test case, test signal that can be used not only as a analysis, as a test case for DSP analysis, but also that can be used in order to verify your access stream interface for your embedded infrastructure, for your embedded environment. In order to simulate CIC Compiler in Vivado 2024.2, the following Python script for workflow automation should be run. Auto, then run sim.py with CIC target. This script will create Vivado project for CIC Compiler simulation, will open the Vivado, and will run simulation. Let's open one more window here, and let's go to the folder with workshop sources. After I run simulation workflow, the build folder will be created. So this build folder consists of Vivado project for specified target. In this case, its a target is a CIC compiler. Besides that, here will be created a log file that can be used in case of Vivado errors. So all errors will be written here. So let's take a look on test bench simulation results. So here I have already integrated CIC compiler, Verilog test bench, and where form viewer. So as a sources, here I have two instances of CIC compiler. One instance for decimation with fixed rate equal to 16. Here I would like to notice that clock frequency is, or sample frequency is 100 megahertz, and frequency of input signal is also 100 megahertz, but the output will be produced on every 16 input samples. So besides that, here I have truncated output in order to keep the same bus width as input signals, namely 16 bits. Another instance, it's a CIC compiler configured as interpolator with fixed rate 16, also 16, like a decimator. But in this case, if we have 100 megahertz sample clock, our input frequency should be 16 times less, so namely 6.25 megahertz. So for implementation options here, numerical precision also I have, since I have 16 bits as input, 16 bits as output will be so here generated. And for this I am using quantization truncation method, so instead of full precision. So beside that, here I have sorry, so besides that, here I have Verilog test bench, where I have integrated two instances without creation, without block design creating. So, and I have here also Verilog header with different test cases, or namely test signals, since this file is common for all IP cores that is used in this workshop. So here as test bench for CIC Compiler, sinus with 1 megahertz frequency is used. So let's take a look on simulation result. So this is the input signal. Can be seen that input signal provides an every clock of 100 megahertz, but output from a decimator will be produced only every 16th sample. So 16 input sample and 1 output sample. So in test bench, I wrote decimator output to interpolator input, and therefore here I am reproducing the input signal. Here, and therefore, of course, since input signal for interpolator, it's with sample frequency 6.25, or in 16 times less than sample frequency. So output of interpolator is provided, as can be seen here, so every 100 megahertz sample clock. So since it's an up conversion. Also here I would like to pay attention on latency. This is an output signal, sorry, this is the input signal. It can be seen that output signal will be a little bit delayed. So this latency, this delay is caused by signal processing latency in both, first in decimator and afterwards in interpolator. So since this bench simulation is completed, several binary files will be generated. Let's take a look in the build folder. In build folder can be found three binary files. So first binary file, this is the input file. So for 1096 samples, and file its interpolation output in 16 times less, since decimation factor is 16, and interpolation output is the same as input. In order to read and plot all these files, the following Python script should be run. Let's go here and in Py folder, and then we can run here CIC Compiler script. So here are three plots can be seen. So first of all, this is the input signal. As I mentioned already, this is a sinus with frequency 1 megahertz. So here can be seen also result of decimation. So for decimation, since we are using factor is our factor is 16, it means that since 6.25 megahertz sample is used here, divided by 2, 3.125. So it can be seen. This is where this signal is defined. And this is the interpolation result. For interpolation result from CIC Compiler, it can be seen the signal is smooth and also yeah, amplitude, unfortunately amplitude is not the same because I did some truncation here, so but amplitude can be also adjusted accordingly. So at least amplitude is the same as it was decimator output. So, and of course it can be seen that the signal here already is defined in 100 megahertz sample clock with 50 megahertz the upper clock here. So, and this is the same 1 megahertz. Let's specify instead of sinus, let's specify a chirp signal. So in order to specify a chirp signal, I will comment this drive sin. I will use drive chirp. Let's move here 124 samples, for example, and the flag is equal, and we have only flag here. So, okay, let's rerun again simulation. That's error. Why so? Let's take a look. No, okay, just we need to restart. Restarting simulation basically allows to run this simulation case. Okay, and let's go. Okay, done. Let's take a look what we have here. So, okay. Yeah, so this is the input signal, and of course, since our sample rate is quite high, sorry, not sample rate, but decimation and the interpolation factor, it's a 16, of course, only part, low frequency part of the signal will pass through decimator and then through interpolator. Let's plot. For doing this, I will run CIC Compiler Py script again. So, and basically the result is the same, that this is an input signal of 0 from 20. So we have the same chirp signal, and this is the decimator output, can be seen here, and the interpolator output. In order to simulate DDS compiler in Vivado 2024.2, the following Python script for workflow automation should be run. Auto run sim with DDS target. This script will create Vivado project for simulation with integrated two instances of DDS compiler IP core. Also, we will need another window to open. Let's go here to, let's go back here. So after I run simulation workflow, build folder will be created. In this build folder, so sim subfolder and DDS Vivado project can be found, since for the workflow, DDS target was specified. So besides that, here can be seen a simulation log file that can be used in order to get information in case of fail of the Vivado IDE. So let's go to simulation result. Okay, it's done. Let's take a look on sources that is used in order to simulate the DDS compiler. For the DDS compiler Xilinx IP core simulation, here two instances of DDS compiler is used. First instance is configured with included configuration option is included phase generator and sinus cosinus loop. So besides that, here I'm using as parameter selection hardware parameters, where I directly define width of my input and output interface. So therefore, also can be used system parameters. For system parameters, these parameters will be defined via spurious free dynamic range and frequency resolution. And depending on frequency resolution, so width of input phase and output data will be specified. So depending on desirable spurious free dynamic range, noise sharpening certain method of noise sharpening will be chosen here. So let's keep hardware parameters here. Okay, with 16 outputs as it was before. So about phase increment. So since I have here phase increment programmably, it means that here should be streaming a phase. But since I have already implemented phase generator in this DDS compiler, it's not a phase. Here I should specify, here phase increment should be specified. So what does it mean, phase increment? Phase increment is a difference between previous and the next value in the phase. So detailed implementation and and summary can be seen here. So this is spurious free dynamic range and frequency resolution. Okay, let's cancel. Let's take a look on second instance of DDS compiler. Second instance has configuration option sinus and cosinus loop. So it means that this implementation doesn't consist of a phase generator, and therefore phase should be created outside the IP core and streamed directly to the IP core. So again, this is a difference between included and excluded phase generator. So in this case here as input we have not an incremental phase, but we have phase itself. So therefore there is no parameter selection. So since parameters is only hardware and noise sharpening, only Taylor series corrected, no phase noise jitter, since phase is controlled outside. For implementation, also phase increment programmably is unavailable here, since it's specified outside, and here can be seen detailed implementation. So beside these instances here, I have DDS compiler test bench. In my DDS compiler test bench, I am using two tasks. The first task in order to generate phase increment for instance with included phase generator, and another task is in order to generate phase itself for instance with just lookup table. Sources for both these tasks can be found in a common Verilog header, and besides that, here also I am using phase in order to generate chirp signal. So therefore, two parameters here specified. It's start frequency and end frequency. For both DDS instances, I would like to generate a chirp signal with start frequency a little bit higher than 1.12 megahertz down to 0 megahertz. So after script finish, output of the DDS IP core will be written in the binary file. So beside that, I have here one more file. This is a AXI wrapper. This AXI wrapper I'm using just for teaching purpose in order to interface the DDS IP core with XCDMA. So in real world, maybe in real application, maybe you don't need this if you are using, for example, the DDS compiler just in order to generate a reference signal, reference waveform. Okay, so let's take a look on test bench simulation results. So first, here can be seen this is a output from DDS compiler with included phase generator. And as can be seen here, phase has only increment or decrement, because we are driving here a signal from higher frequency to lower frequency. So, and unlike instance with included phase generator, instance with only load needs a full phase generator. So this is how basically phase looks like on DDS compiler input without phase generator included. So since test bench is completed in build folder, several binary files were created. So binary file, this is with input phase. Basically, this is a phase for instance only with lookup table, and two binary files. This is the outputs from both DDS instances, DDS compiler instances. In order to run these files, we need to run Python, to call Python and script according to compiler, DDS compiler. Let's take a look. So this is the phase. Basically, this is the same phase that I have here as input for DDS compiler instance, and here can be seen output of from two DDS compiler instances. Basically, what can be seen here? So this is a quite identical signal, so there is no difference. It means that both methods, in order to generate desirable waveform, are working. In order to simulate Xilinx FFT IP core in Vivado 2024, the following script should be run. It's out of folder run sim with the target XFFT, like a name of Xilinx FFT IP core. This script will create Vivado project for simulation, will add Verilog testbench and waveform viewer, open Vivado and run behavior simulation. Let's take a look how Fast Fourier Transform simulation is implemented in Vivado 2024. So in my Verilog testbench, here I have two instances of Fast Fourier Transform IP core. Both instances, it's a runtime configurable FFT. First IP core I configure is a forward or direct FFT, and second IP core is configured as backward or inverse FFT. In my Verilog testbench, I provide input signal for forward FFT, then I use output as input for inverse FFT, and therefore I have here output from inverse or from backward FFT transform. So therefore my testbench writes three binary files. So first binary file, it's input signal. Second binary file, it's an output signal from forward or direct FFT transform, and the third binary file, it's an output from backward or from inverse FFT transform. So configuration of the FFTs, as I mentioned already, it's the same. The most important thing here is it's the runtime configurable transform length. The maximum amount of points is 2048. So runtime configurable transform length means not only number of points, but means also direction, so backward or forward, and also scaling factor for FFT cascade. So by using the scaling factor or so-called scaling schedule, you can control amplitude, or you can control transformation of amplitude during FFT. So other settings here I keep by default. It's the same. So therefore, for runtime configuration, SAXI config interface is used. For input data, it's SAXI interface slave, where I have 32 bits, 16 bits for real and 16 bits for imaginary part. And master interface here also I have 16 bit for real part and 16 bit for imaginary part. Input signal I provide by using Verilog header, so where I can set different signals, but as input in my case I am using simple sinus and cosinus as signals. So let's take a look on waveform viewer. So before I provide any input signal, I do configuration of the IP core. So therefore I am using here a config interface of both instances. In this configuration, I set 1024 points for its a transform length. So this is my input signal, and the results after direct FFT can be seen on these both plots. Basically, this is a spectrum. This is a spectrum of sinus. It's an expected signal, and this signal I provide is input for inverse. And this is an output from inverse FFT configuration. So what can be seen here? So here can be seen that the signal remains the same with the same phase. So it's for real time. This is a cosinus that starts with the maximum amplitude, or let's say like with unit 1. Yeah, and the sinus that starts with a 0. So it's completely the same that I have for my input signal. So it means that there is no phase distortion during both during FFT in both directions. So let's, as I mentioned already, Verilog testbench will create 3 binary files. Let's plot these 3 binary files by using Python script. So for doing this, we will need to go to the folder. First of all, let's check if we have all files here. So yes, we have here. It's input binary. It's a binary file with input signal and 2 output binary files from 2 instances of FFT IP core. Let's run first script. It's in Py. It's XFFT like IP core basically. Okay, let's take a look and plot. So here I have time frequency analysis, time frequency plots for all three binary files. So first, the upper row here, it's an input signal. So here I plot, for example, input signal. It's in a time domain. This is the input signal in time domain, and this is a FFT that I perform by using Python NumPy package. So here I would like to note that its amplitude is around 10,000. It's the same as we have in waveform viewer. So the second row, it's an output from forward FFT configuration. So I plot here without any changes signal in frequency domain. So this is what I have here as output from FFT IP core for forward direction. Afterwards, I perform inverse in order to get time representation of FFT output. So what I can conclude, what can be seen from both these plots. We can see that amplitude is dropped significantly in 1000 time compared to what was on its input. Why so? Because for forward direction, there is no scaling factor. No scaling factor was specified, so and therefore amplitude becomes less in times equal to number of points. So in our case, or number of points or number of transform lengths. In this case, it's 1024. So it can be seen. Unlike inverse FFT configuration. So inverse FFT configuration has this scaling factor, and therefore, if we provide this signal, namely this signal in frequency domain as input for inverse, the amplitude will be recovered. So it will be completely the same as we had here for input signal. So besides that, this plot confirms that there is no phase distortion. So we on output we have here the same signal as we had as an input signal. So and yeah, basically that's all about this Xilinx FFT transform simulation. Let's consider how to handle FIR Compiler in Vivado and Vitis 2024 on development board. So as development board, I'm using Arty Z7-20 board with Zynq-7000. So first of all, Vivado project should be created. Since it's a quite time-consuming process, so I already did this. So To do this, you need to run Vivado Py script. It's a script for Vivado workflow automation with the target FIR. So by running this script in build folder, a Vivado project will be created. It's a build Vivado. So here subfolder FIR with sources. Let's take a look. Yeah, with FIR project itself. And besides that, here in Vivado subfolder, this wrapper XA file. This XA file will be used by Vitis EDI in order to create first platform component for standalone Zynq-7000 and embedded application, standalone embedded application running on Zynq. In order to create Vitis project for both platform component and embedded application, the following script should be run. It can be either run, for example, Vitis PI with FIR target, or it can be done also via GUI interface. Let's do this via GUI interface. Okay, so for GUI interface, select its IP core and afterwards run Vitis. Okay, so Vitis project is ready. So what we have here? So first of all, it's a platform component. It's a Zynq-7000 that is configured as a platform for standalone applications. And besides that, here we have application. It's application to interface DSP IP core FIR Compiler. So here can be found also a source file. Application is already built, so therefore here is ILF file that can be running and launching on the target. Before I start, I would like to open Vivado project, since in Vivado I have implemented Vivado. I have system integrated logic analyzer that I would like to use in order to debug my hardware. Okay, let's start. I have connected development board already, and it's reachable via COM port. This I will need a PuTTY. Okay, so ready. And Vivado. Vivado project is still running. Okay, let's navigate. The project is placed in the Vivado FIR, and this is the FIR XPR. This is our Vivado project. Let's open block design. this wrapper and the block design. As I mentioned already, the Vivado project is created for Arty Z7-20 board, and therefore board files from Digiland I copied into Vivado installation folder. Without these files, you will not be able to build this Vivado. So just note one more time, please copy board files from Digiland to your Vivado installation project directory. So basically how to do this I already point out. So it can be found also information in the readme file. Yeah, with board files I have access here to pins, outputs, pins, peripherals, and so on. That is native for Arty Z7 development board. Okay, so let's take a look at what I implemented in my Vivado design. So first of all, it's like in simulation. I have here 3 instances of FIR Compiler configured for, sorry, not 3, but 4 instances of FIR Compiler configured for different filter types. Namely, it's a bandpass filter, it's a normal FIR filter with hard-coded or predefined coefficients that I have as a core file. So again, configuration is completely the same as it was for simulation. Then I have here decimator, interpolator, and Gilbert. All files, so all 4 configurations has hard-coded coefficients by using core files. So let's take a look how FIR compilers are connected to my processing system. So what I have here, so I have here Zynq Zynq 7000 with 2 ports, so one port, both ports connected to XDMA. So I'm using here XDMA in order to XDMA with 2 enable channels. It's a channels stream to memory mapped and memory mapped, access stream channel, stream to memory mapped, and stream channel memory mapped to stream. So data transfer here is implemented by using XDMA, where I transfer signal from DDR memory to IP cores and vice versa. So besides that, here I have AXI switches. Since all 4 IP cores I am using with only 1 instance of XDMA, I will need to switch output and input in XDMA. So, and for doing this, I am using AXI switches. So AXI switch is configured to have, for example, 1 slave and 4 masters. This is that will feed FIR compiler inputs. And also I have here AXI stream switch that is configured for 4 slaves and 1 master in order to transfer data from FIR compiler outputs to XDMA. Both AXI switchers are connected via AXI Lite interface to my processor, so it's a memory map peripherals, and they are reachable as a just set of registers. So besides that, for Hilbert configuration, I'm using subset converter because filter compiler, yeah, even though filter compiler has 32 here bits output, but really it should be reconfigured, and the reconfiguration can be found here, remapping. So, and yeah, I guess that's all. And besides that, here I have a system integrated logic analyzer in order to check how data transfer occurs, and how data transfer how data pass between IP cores. So it has 2 slots, 2 access stream slots. One slot is connected to stream to memory map channel, and another connected to memory map to stream. So it means that slot 1 I'm using in order to control input signal, and slot 0 I'm using in order to control output signals. Okay, let's consider how to create embedded C application in order to handle CIC Compiler IP core on development board. For C embedded application, Vitis required platform component that can be built by using XA file. In order to export or create XA file, the Vivado project should be built. For Vivado project, the following script should be run. It's run Vivado with a target CIC as a name IP core. So I already did this, and build folder is created in build folder, and in build folder there is a Vivado subfolder. Let's build Vivado, and in Vivado subfolder CIC folder with Vivado project itself and exported sys wrapper XA file. Let's open Vivado project in order to see how to integrate CIC Compiler IP core in the FPGA design. As I already mentioned, as development board, I'm using Arty Z7-20 with Zynq UltraScale Plus. So let's open block design and take a look how CIC Compiler is integrated into FPGA design with Zynq-7000 and how data transfer is organized. So first of all, in order to interface, okay, so here I have two CIC Compiler instances. One is configured for decimation purpose, another is configured for interpolation purpose. Decimation and interpolation here is implemented with rate equal to 16. So it means that sample frequency will be lowered or higher in 16 times, so in case of interpolator. The IP core is connected to XDMA by using two axis stream switchers. It's a multiplexer that allows to multiplex XDMA interfaces, output and input, in order to provide correct data path through a required IP core. Besides that, AXI wrapper is used. So with this AXI wrapper, all data that comes from CIC Compiler will have packet framing. So namely, the last signal and certain amount of samples. Data width for both interfaces for input it's a 16 and as well as for output. So here I operate 16 bits and 16 bits for output. Let's take a look on configuration of the IP core. So as I mentioned already, rate it's a 16 and for output I am using quantization like a truncation that allows me to feed output signal into 16 bits. It's the same as an input. For data transfer, I'm using one XDMA, and as I already mentioned, two axis stream switches that is available for processor by using AXI interface. So this is a kind of set of registers. So muxes or axis switches has, in case of input, it's one slave stream interface and two master, and muxes for output signal, vice versa, has two slaves interface as input and one master interface as output. Let's run Vitis project in order to generate platform component and embedded C application from exported XA file. Yeah, and also here I failed to mention that for debugging purposes, I also have here System ILA, integrated logic analyzer, with connected access stream ports that are connected to XDMA output and XDMA input. So it allows me to check data transfer for input and output of the IP cores. Let's consider how to handle DDS Compiler IP core with Vitis 2024.2 on the development board. So for Vitis project, XA file is required. So in order to get an XL file, we need to synthesize and implement Vivado project. The script for automation Vivado workflow, run Vivado, is used with DDS target. So this script will create Vivado project and export XA file. So I already did this since it's a time-consuming process, and here in Vivado subfolder can be found DDS folder with Vivado project itself and export XA file. So let's open Vivado project and take a look on block design in order to see how to integrate DDS compiler into Vivado design. So let's open block design of the Vivado project that I generated for my Arty Z7-20 development platform. Okay, done. So in block design, I have two instances of DDS compiler. It's the same as for simulation. Both instances is differ by configuration option. So namely, first instance implement here only lookup table, while the second instance is implement face generator plus lookup table. So for in order to transfer data to and from the IP cores, one XDMA is used. So for multiplexing input and outputs of the IP cores, I am using here access switchers. And besides that, here I'm using wrapper in order to interface DDS compiler output to XDMA IP core, XDMA input here. So besides that, here I have System ILA, integrated logic analyzer, that is connected to XDMA input and XDMA output. With System ILA, I am able to see data transfer to and from XDMA. Let's take a look how to implement a embedded C application in order to handle Xilinx FFT IP core in Vitis 2024. So since I'm going to use Vitis, XA file is required. XA file can be delivered from Vivado project. So in order to build Vivado project, Python script for Vivado workflow automation should be run with the target XFFT. I already did this, so therefore here I have a build folder with Vivado subfolder where it can be found Vivado project itself with integrated FFT IP core and exported XA file. So let's open Vivado project in order to see how FFT IP core is integrated into FPGA design. Let's take a look on block design in order to see how FFT is integrated FPGA design with Zynq-7000 processing system. Okay, I will make screen here larger. Okay, so what I have here? I have here only one instance of Fast Fourier Transform. This is a runtime configurable configuration of FFT. So therefore, here I have interfaces for input and output data and configuration interface. Besides that, here I have only one XDMA. So this XDMA has one input. It has one input that will be used in order to retrieve data from FFT IP core, and one output interface. This interface is shared between FFT input for data transfer and for configuration channel. So therefore, access stream switches or access stream multiplexer is required here. So therefore, here multiplexer has one slave and two master. One master it's directly for data, another master it's for configuration interface via subset converter. So here I'm using subset converter in order to adjust output data from XDMA, adjust to configuration port of FFT transform. So besides that, here I have System ILA, integrated logic analyzer, and as usually, so it has two AXI stream ports, AXI stream interfaces. So one interface, one port is connected to XDMA output, another is connected to XDMA input.